For equations of motion, give myself a little bit more room here. Some moments about O. What do we have? Shall we go ahead and do our different weights that we would have? Our weight of B, cosine theta. Yep, I'm gonna go ahead and I just sitting there thinking of what I would want to use for my positive or negative. That if we use our, we'll call it right-hand sign convention, when we're dealing with path coordinates, on our coordinate system that we use for path coordinates, we have tangent and normal, and the tangent cross the normal creates a binormal. So the binormal direction, for this case, the way we have our tangent and normal defined, we'd be going into the board. So if I wanted to go ahead and use my right-hand rule for what's a positive moment, I would actually say clockwise is positive. That's why, because a tangent cross the normal gives you your binormal direction, so to speak, the perpendicular axis to the plane of motion. And so we define it as long as we define our, we'll call it positive direction, we can make sure we're doing our moments correctly. So there's a question about that we have two couple forces at 150 newtons. That is correct, but our space in between. So I'll go ahead and illustrate. We had our 1 centimeter here for one force, and we had another centimeter here for our other force. So we can do 2 times 150 times 1, or we can do 150 times 2, is where you get that. So we need to, on our equations of motion that we're working on here, now that we defined our direction, I'm going to go ahead and sneak in my minus sign for that weight of B. And we have that distance there of your 22.5. The weight of A, we're saying, is in the middle of the arm.
Excuse me, Dr. D?
Yes, sir.
You're saying that the joint is like 1 centimeter away from the end, but I see the drawing that's 2 centimeters.
The center point of rotation.
Oh,
it rotate, since I got two forces, you know, equal and opposite, they're 2 centimeters apart.
Okay.
So the point of rotation is going to be
1 centimeter.
Yeah, it's going to be 1 centimeter from the end of the arm.
Oh, okay. Okay, thank you.
So that's why I put 0.0 at the point of rotation,
okay,
so that we just include that one moment.
Thank you.
So I think we're good to there. So now we need to do our weight of A. Cosine of theta. And as far as its moment arm, looks like we would, yeah, we can just do the half of the 22. So we'd have 11.125. Plus our moment we just figured out. Looks like we got all of our moments about the 0.0. So what do we set that equal to? Sum of your moments, now that you're doing equations of motion, sum of moments is going to be our mass moment of inertia about that 0.0 and its angular acceleration. So all we need to do now is figure out, well, okay, what is the mass moment of inertia about 0.0 for our swing arm with its object? So you have here, there's I guess a couple of ways you can look at this. As far as, I'm going to go ahead and call this a rod. The expression for the mass moment of inertia works out the same. Your ball, of course, is a sphere, but basically for our IO, mass moment of inertia about 0.0, we're going to do the summation of our I's about G, the center of gravity for each of the objects. We have two objects, plus their mass. So maybe I should go ahead and put this IGI, the mass of I, and the R of I squared. We're summing up those two objects. So what are those two objects? We got the IG of the ball. Go ahead and scoot this up a little bit. Plus the mass of the ball. And I'll just go ahead and say RB. We'll label it as RB. We need to figure out what that is. IG of the arm plus the mass of the arm and this distance from O. So there's our expression for the mass moment of inertia for the swing arm with the ball installed. Basically, we're treating the object as the sphere and the arm are together, doing the launching, we'll call it range of motion. And of course, once it reaches 60 degrees, off it goes into the wild blue yonder. So on your, let's go ahead and see if I can slide this over here. Your equation sheet.
Dr. D.
Yes, sir.
On our diagram for this project, what is it showing is at 6 centimeters?
6 centimeters is we'll call it when it's resting before it launches. It's resting on an arm, and so as it goes up at that angle until it reaches to the, we'll call it the, I guess I won't call it a stopper, but anyway, it reaches the end piece that causes it to rotate. But as soon as it rotates, as soon as it raises up to where it hits that end, then it comes off of that resting bar. It's just a resting bar. It's just resting there as it moves up while the propeller is, we'll call it, spinning.
Okay.
As soon as it gets up to the top and it starts launching, then it comes off that resting bar and it pivots and launches the ball.
So that resting bar isn't considered one of the forces?
It is not. Since it's not pinned to that bar, it's not included in our free body diagram. All we have to do is model everything, we'll call it, around the pivot point.
Okay, so but there is another force that comes from underneath that's 1 centimeter to the left of it?
No, there's not. That 1 centimeter, again, from the end is just to figure out if I have two couple forces, the 2 centimeters, that's where you get your two forces applied to the swing arm. One of the forces is applied at the very end. Another force is applied 2 centimeters inboard of that. And so because those are equal and opposite, that creates that, we'll call it direction, or creates that moment and rotates it.
Okay.
So you might want to watch the demonstration again to, be clear on how we're.
Okay, yeah, I understand the one at the tip. I was just confused about the one that was on the basket side.
Yeah,
of it.
the other one is just a one that it rests on until it reaches whether it's pushing on the end and then launches the ball.
Okay.
So it doesn't come in play in our dynamics. So on your equation sheet, what I'm showing here, I'll throw this up big real quick. We have our two equations for a sphere and a rod, or basically the equations that we're using to figure out those IG terms are 2/5 and 1/12 is what we're using there. So one thing I don't think I put in the assignment sheet is what your radius of your ball. And your diameter of the ball is 3 centimeters. So I was wanting to check yep. So let me go ahead and indicate that your R of B, and I'm going to get I better call it R of S. The radius of the sphere is 1.5 centimeters. Because we're coming in here, what we just had for the sphere are 2/5 mass of the sphere that you know, radius of the sphere, and yep, these are squared. So I'm mixing subscripts here. So let me at least keep this part straight. Mass of the ball, radius of the sphere, which is the ball, mass of the ball. How far is the ball from O? Looks like that's our 22.25. And you might want to make sure you're using we'll call it consistent units here when you're figuring these out. Then we have our arm. Arm we're going to model as a slender rod. Whether you model it as a thin plate or a slender rod, you basically get the same relationship for IG. You get your 1/12 mass of that arm, and its length, and its overall length is 23.25. And of course you have its mass again. How far is it from O? That's where we get our 1/2. Okay. So everybody good with how we have our equation of motion set up? So with that, just like, okay, fine. That looks all real neat and impressive. We know how to set up equations of motion, but how do I get the range of the catapult? How do I know how far it's going to throw the ball? If we know these equations of motion, and I'm going to put it here, that I have an equation now that I have a moment. Let's write it this way. Minus my weight of B times our 22.25 plus our weight of A and so the weight of A was our 11.125 times the cosine of the angle is equal to that IO alpha. Okay? So you have an expression for alpha. Alpha is 1 over IO of this expression. And left out my 1. So I'm going to, for notation's sake, I'm going to define a, we'll call it K here. And I would think it'd probably be best to say that K is our, I'm going to illustrate it this way, that I'm taking this right here, I'm saying that K is that expression. Now I'll just call it K. Let's write it that way. All I'm doing is trying to simplify my notation here. And I'm going to call that expression there K. That you have, again, alpha is equal to your moment divided by your applied moment, IO, minus this K over IO cosine theta. Okay? So what is the relationship between your angular acceleration, displacement, and your angular velocity? How do we figure that part out? And so I'm going to go ahead and move up here. That my relationship between angular velocity, angular acceleration, and angular displacement is that omega d omega equals alpha d theta. You now have an expression that is equal then to my m over io minus that k over io cosine theta d theta. Where we're heading here is I need to know the velocity of that ball when it launches at 60 degrees. We start at 30 degrees. And I'll indicate it this way. We launch at 60 degrees. So how are we going to get our omega? See if anybody can give me a hint.